Hello, this is Yahweasel. So, a number of people have asked for a sort of technical discussion of Craig, or a technical description of Craig and how Craig works. If you're not aware, Craig is a recording bot that I wrote. It records Discord and recently web app conversations as well. So it's a recorder. It records audio coming to it out of Discord. That's what it does. So, a number of people, as I said, have asked for a sort of technical description of Craig. And I've been a little bit reluctant because it's not like I invented any of these concepts. I just sort of put them together well. I just know what I'm doing. But that's, whatever. Fine. I'll do a technical description, and I'm going to do this in video form rather than in sort of text because, again, I didn't invent any of this, so I'm just describing to you how Craig works rather than sort of so I'm whatever. Anyway, I have no excuse. I'm doing this because it'll be easier. So, Craig records, and there have been many competitors to Craig. Craig records Discord, but there are competitors obviously using other systems. If you are recording voice over IP, though, then there are particular caveats, particular issues you have to deal with that you don't have to deal with while, say, recording a microphone locally. And many of Craig's competitors have not known the right thing to do to deal with the unique situation of voice over IP. So let me try to describe to you what that situation is. Normally, when you record audio, you think about it as a stream. So certainly analog audio is literally a stream. It's just the electrical voltage difference along a chord as it continuously comes. In fact, to analog audio, that's the electrical sense of it. Obviously, analog audio, as in audio in the air, is just the continuous motion of, or the continuous waveform moving through the air, the pressure wave through the air. And it is natural when you move into the digital domain to also think of it as a stream. Digital things are digital, so it's not going to be a continuous stream in the mathematical sense, but there is this concept of a sampling rate, and if you sample 48,000 times a second, then you expect to receive one sample every 1 over 48,000 of a second. And fine, as long as you're receiving it at that rate, that is your stream of audio. And if you want to record something like voice over IP, something where you have multiple sources coming from different systems, different computers, and your first, I was going to say first, and the abstraction you choose to use is to record streams, you're already dead. You're already dead. That step one, the very first hurdle, you have made an unrecoverable error if your first thought is audio is a stream. And it's terrible. It's like if you make that decision, you're dead. You cannot fix that. When you're recording audio over the internet, over anything where you have a remote connection, or even, frankly, if you're recording audio from multiple devices on the same system, you cannot think of it as a stream of audio. You just can't. And there are two particular reasons. One of them is, and this applies whether it's multiple on a local system or over the internet, what's called crystal drift. So I have multiple things all attached together here. Maybe I have a discrete sound card. I have a USB microphone amplifier with an XLR mic plugged into it. So my sound card, my computer itself, and this mic amplifier each has their own timing crystal in it, as in a little piece of electronic doodadery that keeps the current time. And the probability that they are 100% in sync is 0. Of course they're not 100% in sync. It's impossible. So if I'm recording something from my sound card and something from my microphone at the same time, and I'm just treating them as streams of audio, they will slowly drift out of sync, inevitably. It's literally unavoidable. Typically, if we're talking about the same system, it'll take a couple hours before they're noticeably out of sync, but still, that's a couple hours, not, all of time, it really doesn't take that long for them to get noticeably out of sync. And when there are multiple systems distributed across the internet, where things tend to be a little bit less consistent, it's not at all unusual to get as much of a second of desynchronization after even an hour and a half, something like that. And that's obviously unacceptable. So you can't think of it as a stream because it is natural to think of streams as being at the same rate, and they're not. The other part is, if this is over the internet, you are going to only receive audio data when there is audio data to receive. So if on voice over IP, when you're not speaking, typically it's not sending any data. This is called voice activity detection. It's only sending data when you're actually speaking. So you don't get sort of a continuous stream of audio, you get these bursts of audio. And any library that's presenting that to you as a stream is inventing the silence in between. It's actually creating extra work for you to handle that silence. So, and on top of that, even if you understand the fact that you're only receiving it when they're talking, a typical voice over IP application uses UDP. I'm not going to go into a lot of detail about that, but the point is it's not reliable delivery. Which means you're not actually going to receive every voice packet. You'll probably receive most of them. You'll receive the majority, probably the vast majority, unless they're on a very bad connection. But you won't receive all of them. So even during the bursts of speaking, it's not necessarily a continuous stream. So what do you do when that's the situation? Well, you do what Craig does, or you do what Podbot did. By the way, Podframe, which now doesn't exist, was probably the major competitor to Craig, but I'm going to distinguish here. Podframe was just an instance of a bot written by somebody else called Podbot. Podbot still exists, but it's not public, and it also does it right. And these are the two bots for Discord that do the right thing. So what do you do when you want to do the right thing? Well, let's go into a recording session and look at the code for receiving a chunk, that's encoding a chunk. Let me just, there we go, on receive. So first off, it has to make a track. If the user doesn't have a track, it's storing things like the username and storing the user avatar if necessary, blah, 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 blah. And once we have a, track, then we take the data and we add it to this user recents. And the reason why we have user recents is that with UDP they could be received out of order. And so we have to put them back in order. Luckily, it at least tells you what order they should arrive in, but it's your job to actually make sure that they're in the correct order in the first place. If your API is naive and just sort of it decodes things as it gets them, you'll get garbage here. The normal client, if it receives something out of order, then it adds a delay so that it can buffer things and put them back in order. That is essentially exactly what we're doing, except we don't really need a delay per se, since we're just recording anyway. We're not outputting the sound. Once we have enough data, we flush that out. Flush is up here somewhere. And that encodes the chunk. And the important thing here, so I'm using a file format called OGG. You're probably familiar with OGG for the Vorbis codec, but OGG and Vorbis are distinct things. Again, I don't want to go into too much detail, but a codec is how you encode audio or video data. A format, a file format, is how you store that, and it is typically part of the format that indicates the timestamp. So the time when a particular piece of data is supposed to arrive. I like OGG a lot because it's an unbelievably simple format, and so I can have like a tiny bit of JavaScript to do this for me. But the important thing here is OGG keeps the exact timestamp of every single chunk of audio. In the context of a audio format, that would typically be called a frame of audio. Coming over the network, it's a packet of audio, whatever you want to call it. In Opus on Discord, it happens to be 20 milliseconds worth of audio, which is 960 samples. This is all details that aren't that important. The point is, we're not thinking of it as a stream, we're thinking of it as individual chunks. Each of those individual chunks could be out of order. We can reorder those chunks, write them independently to the file, and each one of them has its own timestamp. So we're not treating it as a stream, we're treating it as individual chunks, each of which has its own timestamp. In code chunk itself, let's see here, there's really not a lot to be said. This is all just guff. This is all just garbage. This is, if Discord is sending us random trash, then we slice it off. Occasionally we check that it's actually an Opus packet and tell them if it's corrupt, and then finally we actually write it out. And write is not that complicated. It just writes it to the stream with the granule position. The granule position is the timestamp I was talking about, and that's about it. So Craig actually produces valid OGG files with Opus data. It never decodes the Opus data. Every 50 packets, it decodes it just to check if it's corrupt, but setting that aside, it never decodes the Opus data that Discord gives it. It just assumes that the Opus data is correct and writes it out to the disk. So what Craig is actually creating is an OGG file that is technically valid, but doesn't have streams of audio. It has a bunch of independent chunks of audio, each of which are timestamped. That's a valid use of OGG, like this is a valid OGG file. OGG files are allowed to look like that, but no actual decoder, no actual piece of software will handle that correctly. ffmpeg, I don't think I have ffmpeg installed on this system. 1 second, let me fix that. ffmpeg, if you really cajole its resampler, can sort of be convinced to handle a file where it's a bunch of individually timestamped chunks. It, by default, assumes the opposite. It assumes it's going to be a stream of audio, which is fine. That's not a complaint about ffmpeg. It's incredible that ffmpeg even can handle the weird case, because almost all audio is in streams, and that's fine. But to do this in ffmpeg, ffmpeg can do it, but it's like a really weird command. We have to make sure that we copy TS, that's copy timestamp, send it through a resampler, and then there's like a very careful invocation to make it do the right thing in the resampler, which is nothing like that. That was the sort of simple version that isn't actually going to come out good, and then you could actually output a file. But it's very, very expensive in ffmpeg because ffmpeg just wasn't meant to do that. Again, not a complaint about ffmpeg. I love ffmpeg more than you can possibly know, and ffmpeg has nothing to do with mpeg, by the way. Just, to confuse that. I don't know what the ff stands for, and it has nothing to do with mpeg, so great. I love ffmpeg. It does great things. It doesn't really solve this problem, though, because with enough cajoling, you can kind of get it to work, but it doesn't actually know what the input is. It just gets confused. So I have this little program called Augustender. It's being highlighted weird. It's chosen to put those in a different color. That's weird. Do I not have like C highlighting installed? Whatever. This is not my normal system. This is a virtual machine just to demonstrate this on. This is Augustender. Augustender's job is to extend an OGG file that has these individual chunks to almost have a stream. Not quite a stream. We do count on ffmpeg's resampler to handle minor errors. We handle the big chunks of empty space, because that's what ffmpeg was really never meant to do, just fill in giant chunks of empty space. It can handle little irregularities in the timestamps just fine. So all this program does is it reads in OGG headers. It does not use libOGG because OGG is really, really simple. You don't need libOGG to read OGG files. This is OGG. That's all there is to it. I love OGG so much. It's so simple. It's such a simple format, and I love it. Anyway, so we read in the data. There's some technicalities here about how I handle data that normal OGG files would need to be a little bit more normal OGG processors would need to be a little bit more wise. I happen to know that Craig's output is restricted in several ways. We handle headers. I might talk about that a little bit in a moment. We handle Opus or FLAC. This also has to do with FLAC, and nothing else. And if it's not a header, then it's the actual data. There's more obscure nonsense that comes from Discord. Thank you so much, Discord. And then we account for gaps. So the granule position, as I said before, is the timestamp. So if the granule position is greater than whatever Augustender's internal notion of the granule position is, plus some number of packets, only 1 if the last was silent, 5 if there still is sound coming in. So in other words, if we've skipped some amount of time, more time than we expect to have skipped, then we're behind. If the last was silence, then we only insert, if the last was silence, or if there's a really large gap, then we actually insert real zeros, as in silence. And we are trying to turn this into a stream of audio, so we literally just, in a loop, create packets that are 0 packets, which is to say packets containing nothing but silence. So we're still treating this in a packetized way, but we're getting closer to a stream just by injecting more parts of the stream. And it's worth noting here that true granule position here, this is our sort of streamy granule position. The internal granule position, this is the actual timestamp. This is when the data arrived. So we're trying to rectify this difference between real time and stream-like behavior, and this is most of that rectification. If there wasn't a real gap, then we have to correct timestamps. We also account for the opposite direction if we have too much data coming in, where we have to correct timestamps the other way. If we correct timestamps, well, either we're done, we've gotten up to the right amount of time, or we add a little bit to our granule position. This is non-stream-like behavior. We're now outputting timestamps that don't correspond to the amount of audio data, so this is packet-like behavior rather than stream-like behavior. But we can pass that through to ffmpeg, which can do the right thing. Then, finally, we actually write it out. There's a little bit of trickiness for FLAC, but yeah, for the most part, we just write it out. So this converts aug to aug, but in doing so, it fills in the gaps and tries to account for places where the timestamps don't quite seem to make sense, by sort of making timestamps that are trying to catch up with the timestamp we actually received the audio. So, the important thing here, the critical thing here is, this is our real timestamp. This is the timestamp when we received the audio, and there's only one timestamp source for that. It's the computer that received the audio, the computer that's running Craig. I don't care what your microphone thought the time was. I don't care what your computer on the other side of the internet thought the time was. I don't care what anybody thought the time was except me. I know a granule position. It was my system time when I received the data. As long as I'm only using one time source, I should always be in sync. So this is all to bring the vagaries of the actual time source, whatever the system that is talking to us thought the time was, in line with the real time source on our system, and in line with the notion of a continuous stream of audio. That's Augustender. This, honestly, this is the heart and soul of Craig. This is why Craig works. And it's not a huge amount of code. This is 300 lines of code. Like I said, this is, none of these ideas are things that I invented. I just know what I'm doing. So, you know, it doesn't take a lot to do this right, but you do have to do this right. This is in C because it needed to be fast, but it's not complicated C. This is really, really simple C code. Like, yeah, if you call yourself a programmer and you look at this code and run away screaming, then maybe you're not such a programmer. Anyway, so Craig audio is cooked. The cook script is as in processed. It's processed because ultimately what I deliver to you is streams of audio. It's just streams of audio that are all correctly timed. And so I'm reading in all of this stuff that isn't correctly timed. It goes through Augustender and gets cooked, gets processed into something that is a stream. The only thing I really want to show you here is, indeed, we are using ffmpeg to do the resampling here. Max soft comp is how much we're willing to stretch or squeeze the audio. This is essentially the roboting effect that you usually get. It's slightly better here because we're doing it post hoc. We're not doing it as we receive the audio. But the sort of amusing thing here is this is just an arbitrarily large number. just always use stretching and squeezing. The reason it's fine to do that is it's already ran through that Augustender, so it's only going to be off from the time, like the timestamps are only going to be off by a tiny, tiny fraction. So it doesn't matter how large we set this value here, Augustender is providing the right input. If I wanted to actually only use ffmpeg, I would not set it to that. I guess the only other thing worth noting here is, yeah, this is a shell script. You know, there's one thing that shell scripts are still vastly better at than literally any other system, and that's just piping a bunch of programs together. All this does is pipe different programs together, move their input and output through each other, ultimately piping Augustender. Let me get down to where it's doing something. Piping Augustender. I'm surprised I haven't found Augustender yet. There we go. Piping Augustender through ffmpeg, through something that just sets the duration correctly. This is really trivial just because some files don't like having weird duration set, through an encoder, and that's it. That's all it does. It's just piping things through a bunch of these phases, but the important thing is the input is just junk, basically. I mean, it has all of its timestamps, but it's not a stream of audio. It's just a bunch of individually timestamped things. Augustender brings it closer to that. ffmpeg does the last fix-ups for anything where the timestamps are just slightly off, and now we have only one timestamp source. And that's what we wanted. Everything is inherently in time with everything else. It can't fail in that sense. The only other thing I wanted to mention, oops, it just called Craig/rec. I don't know where I'm trying to go. The only other thing I wanted to mention is the other benefit of using this technique is, since I'm not decoding the audio, at least not most of the time, just for debugging, I have this occasional decoding, but since I'm mostly not decoding the audio while I record, Craig is so inexpensive. Like, Craig itself is extremely cheap to run. But there's a disadvantage too. So, mixing, if you take a random Discord API that offers you audio off of the channel pre-mixed, it's gonna sound no better than it does out of Discord, because it can only do what Discord can do, but because it's receiving that data live, it knows what audio is actually sounding. It's not worried about the fact that, oh, there is this other stream that isn't making audio right now, but, you know, I have to fill in that gap with silence. Only the audio that's there is there. So mixing is actually way, way less expensive to do if you do it here, if you do it live while you're receiving the audio. And so if your goal is to mix, you wouldn't make Craig. You would make a totally different design. But then if your goal is to mix, you don't need Craig. You can just record the output of your computer. You know, Discord itself does it just fine. But the caveat to that is, well, when I want to mix, which I don't, but when I want to offer mixed audio, which I do to patrons, that's really, really expensive, because it has to go every track through this independent process, and then I'm mixing a bunch of silence. Every track is a complete stream, and all being mixed together. So the time when you convert it from packets into a stream really, really matters, but if you just make the wrong decision, you are painting yourself into a corner. You have to know when and why you're converting from packets into a stream. And for Craig, I made a decision to convert packets into a stream very, very late. Very, very late, but before mixing. There we go. But the caveat to that is that mixing becomes more expensive. Mixing is easier to do when it's packets, not a stream. But I get better quality single-track audio because I'm doing it late with the timestamp data and post-hoc. Finally, let's take just a moment to talk about I was about to say Craig's latest feature. Is it Craig? It's about this other project that I've done that also relates to Craig. So Craig offers this as a feature, but I would say it is sort of independent of Craig. It's OnWeCaster. So OnWeCaster is a web application by which you can send audio to, right now, Craig. Craig is the only OnWeCaster server, but as a web application, it could notionally hook up to anything. I have definitely made changes to this in 2019. Don't you, programmers who maintain copyright headers like this, don't you hate the first month of every year where you're constantly updating your headers? Oops, I changed that this year. Anyway. So OnWeCaster is multi-user synchronized recording via the web. The important thing about OnWeCaster is it does the same intelligence to do with synchronization. You must trust only one synchronization source. This is the reason, I should say, I haven't used Zencastr, but a lot of people who come to Craig complain that Zencastr lost synchronization. And I assume, by my understanding, that this is the reason why Zencastr loses its synchronization. They are trusting different synchronization sources, different clocks, to be the same. But they're not the same. They're different. What OnWeCaster does is it has a connection to the server that just pings, a ping socket, and the point of the ping is it sends, do I have a ping function? Function ping. It sends the timestamp in JavaScript vernacular performance.now. It sends its local timestamp along with a ping. When it gets a pong, the server sends its timestamp, and it rectifies that difference. So the client, it has to use its local time to know when audio data is coming in locally, because what else is there? But it is constantly rectifying its local time with the remote time. So if my clock is running slow with respect to the remote clock, then I will constantly be updating my time offset to bring my sort of virtual clock exactly in line with the remote clock. Same if my clock is running fast, whatever. Since I'm constantly updating this time offset, I'm always getting the right time. But the caveat of that is it's not a stream anymore. I don't have a continuous stream of audio. I have a bunch of individual packets of audio, each of which gets independently timestamped. I'm trying to see if I can find where it's actually getting timestamped. Doop-a-doop-doop-doop-doop. I mean, it's granule position again. Yep, there we go. Granule position. And then we adjust that timestamp by the time offset to make sure, as best as we can, that it is related to the server. But because we're adjusting that timestamp, it's just not a stream again. And so again, we keep things in sync by eschewing this notion that audio is a stream. Audio is a bunch of packets. That's such a critical thing to understand. Audio is a bunch of packets if it's digital audio. Thinking of it as a stream, if you're recording one source, that's the right way to think of it. If you're thinking of it as multiple sources, you have to throw that thought away and think of it as a bunch of independent packets. The only other thing sort of worth mentioning with OnWeCaster in particular, so I talked about there's a voice activity detector. You're only sending audio when you're actually speaking. That's normal for all voice over IP applications. That is also the normal behavior for OnWeCaster, but OnWeCaster has an option to send the data continuously, to send it at all times, even if you're not talking. This has a benefit if you want to edit it. If your goal is to just take the data and throw it together and be done, you actually want a voice activity detector because then you're not going to get all the background noise. If you are going to edit, then you're going to try to edit the noise out, and to edit the noise out, you want a clean noise sample, which means you want all of the audio data. Slightly weird. Anyway, but the point, what I'm trying to make is, when you're recording continuously, we are now in this odd edge where we're actually recording a continuous stream and then trying to turn it into a bunch of packets and then trying to turn that bunch of packets into a continuous stream, which is slightly weird. And the way I get away with that is I run the VAD, the voice activity detector, always. Even if you're recording in continuous mode, you are being recorded with a VAD. But if it is in continuous mode and the VAD is off, you still send the same audio data, but you send it with this extra piece of information that says, by the way, here's the audio data, but he wasn't talking right now. There was no actual sound. I expect this is garbage audio data, but here it is. Why does that matter? Well, if we go back to good old Augustender, I have a special mode here, which is the OnWeCaster VAD data, where we're going to get extra VAD information. And the nice thing about having that VAD information is we can detect whether the last was silence. If it was below our VAD level, then it was silence. And thus, we can use that silence information to be wise about how we insert gaps or cut out audio. So, so even though it's continuous, I am still treating it as a bunch of independent packets and just trying to preserve as many of them as possible. However, I at least know which packets are not as important to preserve. It's the ones where you weren't actually talking. And so I'm willing to just dump audio packets where you weren't talking. If you're sending too much audio data because your clock runs faster than mine, I'm willing to add gaps where there's no sound at all. If you aren't talking at the time, if you are being silent, in which case I'm going to take your kinda silence of whatever the background noise is and add true silence of actual sort of zero data, but that's fine. I'm only doing that when you're actually silent, or if there's some major issue and a big gap in there. Okay. So, the lessons to anybody who wants to write something similar are, do not think of audio as a stream. You must ultimately make a stream to give it to the end user. And as you're thinking of audio not as a stream, make sure that whatever timestamps you're using, whatever way you're independently timing every individual packet, make sure you only have a single source for that timestamp. Do not trust multiple sources to stay in time. And of course, once you've gotten all of that data together with everything independently timestamped, you're going to need something like Augustender to turn that back into a stream. I don't know of any other program in existence that does exactly what Augustender does, but the fact is, of course this has been written before. It's just that it's actually kind of trivial. It's 304 lines long, so it's just not actually that difficult of a problem to solve. It's such a trivial problem that there's no program out there to do that, because you just write one when you need it. It's sort of not, it's not complicated enough. So, I would love for there to be more competition for Craig. There's not a lot. If you want to write competition for Craig, please understand digital audio and understand the fact that it is not a stream. Understand how to timestamp audio with the actual, with a single clock, usually with the receipt timestamp, because that's, you know, this, you can trust the one clock of whoever is receiving all of the data. Make sure you understand how to timestamp audio so that you're not treating it as a stream, and everything is timestamped with the same clock, and how to then transform that back into a stream. That is the way that you write something that gives you the quality of Craig. That's also the way you write something that's just inexpensive, that's inexpensive on the CPU while recording. It's just the right way to solve this problem. Unless what you want is to pre-mix. If what you want is to mix things immediately, you need a different solution. But anyway, I would love for there to be more competition for Craig. I hope that this explanation of how to actually do this helps someone. If you have other questions about why it works this way or how it ought to work, comments below. That's fine. Thanks for watching. Cheers from Yahweasel. Quick addendum, so if you do want to be a competitor for Craig and make your own digital audio recorder for some kind of voice over IP system, I definitely encourage you, for the love of God, don't use f***ing MP3 in 2019. MP3's competitor was cassette tapes. It's obsolete, and the format that obsoleted it is also obsolete, and the format that obsoleted that is also obsolete. Just stop! If you're going to make a digital audio recorder, learn the first thing about digital audio. Like, one thing. Don't use MP3.